We're going to start talking about trigonometric identities. We're going to learn some more identities. You're going to be responsible for knowing these. The ones that we're going to go over today, you pretty much know these reciprocal identities. We worked with these when we were doing the unit circle. We know that cosecant of theta is 1 over the sine of theta. We know that secant of theta is 1 over the cosine of theta. We know that cotangent of theta is 1 over tangent of theta, but that also means, remember, that it is cosine over sine. And of course, the tangent of theta is sine of theta over cosine of theta. Those we pretty much already know. Now, you are responsible for knowing them and being able to use them on quizzes and exams from this lesson forward, but we've worked with them enough. I don't think you're any longer confused over which cofunction these go with. Now, the Pythagorean identities are new. They are new to us, so let's take a look at these Pythagorean identities so you get a good idea of what's going on here. The Pythagorean identity itself is this one right here. It is the sine of theta quantity squared. Remember, that little squared in front of the angle measure means the whole thing is squared, plus the cosine of theta quantity squared. And that equals 1. Now, there's a whole reason why that's true, and it all goes back to the unit circle. Remember, in the unit circle, our x coordinates were our cosine, our y coordinates were our sine, and we're in the unit circle, which means our radius was 1. So this all goes back to the equation of that circle. And the equation of the circle with radius 1 looks like this. If it's centered at 0 and has radius 1, here is the equation of the unit circle. Since all of our x coordinates are cosine and all of our y coordinates are sine, this makes the Pythagorean identity true. Not that you need to know that, but that's where the Pythagorean identity comes from. It's not coming out of, nowhere. It's absolutely there. Now, these two Pythagorean identities come about by taking this one, the actual Pythagorean identity, the Pythagorean theorem, and dividing each term by the same trig function. Let's take the sine squared of theta plus the cosine squared of theta equals 1, the Pythagorean identity, and let's divide each term by cosine squared of theta. I'm not changing the value because I'm doing the same thing to each term on both sides of the equal sign. So I'm just dividing each term by the cosine squared of theta. Now, we know that sine over cosine, which also means sine squared over cosine squared, equals tangent squared. So that's where this one comes from. That's where this term comes from. Cosine squared divided by itself is 1. That's where we get this term. And 1 over cosine squared is going to be secant squared. Excuse me. So this doesn't come out of the blue either. This is using some algebra to change the form of the Pythagorean theorem. And we want to do that because sometimes we want to use these theorems to simplify things or to prove things, and things are not always given to us in terms of sine and cosine. Sometimes they're given to us in terms of these other trig functions. So these alternate Pythagorean identities come in handy. This one comes about by taking this Pythagorean identity and dividing each term by the sine squared of theta. I'll just show you that really quick. So if we divide everything by the sine squared of theta, first of all, we're going to get 1. Sine squared divided by itself gives us that 1. Cosine squared over sine squared is cotangent squared, and 1 over sine squared gives us cosecant squared. So make sure that you know all of these Pythagorean identities. Basically, what you have to do is just memorize this Pythagorean theorem in terms of sine and cosine, and then the other two you can come up with by dividing through each term either by cosine squared of theta or by sine squared of theta. And you'll see as we work some examples how those come in handy. So why are identities important? Trig identities enable us to write the same expression in different ways. It's possible to rewrite a complicated looking expression into a much more simple one. So to simplify algebraic expressions, we used factoring, we used common denominators, we used all these special formulas where we could simplify our expressions so we could see what was going on. We're going to do that same kind of idea by simplifying our trigonometric expressions, but we're going to use these fundamental trig identities. And the ones we're learning today are not the only ones, they're just the beginning. So let's say we're given the expression cosine of t plus the tangent of t times the sine of t. And we really want to simplify that expression. So we start by rewriting it completely in terms of sine and cosine. We can see here this is already cosine, this term is already sine, but we know we can rewrite tangent in terms of sine and cosine. It is the ratio of the sine of t over the cosine of t. And you can see that we can multiply our sine of t's together. That's how we get sine of t quantity squared. So we have a common denominator to both our terms. If this is going to have a denominator of cosine of t, this term needs a denominator of cosine of t. That's why this is cosine squared. And notice what's going on in the numerator. Do you notice what that is? That's our Pythagorean theorem. And we just learned that that equals 1. So anytime you see cosine squared plus sine squared, that's plus. Be careful. Cosine squared plus sine squared, or sine squared plus cosine squared. You can replace it with 1 because that's what it is equal to. We'll go back here and look. Sine squared plus cosine squared equals 1. So anytime you see that, you can definitely simplify that by substituting or replacing it with a value of 1. And we know that 1 over cosine is secant. So we went from 3 terms, one of them a product, to 1 single term that we could use and do some mathematics on if we needed to. Now here's kind of a complicated looking trig function. We have the cotangent of theta squared over 1 minus the sine of theta squared. We know that cotangent can be rewritten in terms of sine and cosine, so let's do that to try to simplify things. That's going to be cosine theta squared over sine theta squared. And we haven't done anything in the bottom here except rewrite cosine squared of theta. If the cosine squared of theta plus the sine squared of theta equals 1, then 1 minus, if I subtract sine squared of theta from both sides of this equal sign, it has to be true that the cosine squared of theta equals 1 minus the sine squared of theta. So we took this expression and rewrote it as cosine squared. Now they've put it over a 1 to show you that you have a fraction over a fraction, so that you will take that bottom one and flip it and multiply it. And look what happens for us. That simplifies quite nicely to 1 over sine squared, which we know is cosine squared of theta. So it looks complicated, but we just use those identities to simplify and replace what's going on in those expressions. Now let's talk about proving trig identities. Proving is a pretty important mathematical term. I don't want to glean over the word proving. Proof is a big part of mathematics. It turns out, thank heavens, that it's not a great big part of calculus, but it is a big part of trigonometry. So we're going to look at proving trig identities, and there's some rules we have to follow when we're going to prove something is an identity. So many identities can come from or follow from those fundamental identities that we looked at. In some of the examples, we're going to learn how to prove that a given trig equation is indeed an identity. And by identity, mathematically, we mean that is always true. If it is an identity, it is always true. So let's see how we can prove something is an identity. It is a three-step process. So let's look and see what we should do. The first thing we should do by following the guidelines for proving identities is to start on one side of our equation. We're going to have something equals something else. We're going to have a left-hand side on our equal sign, and we're going to have a right-hand side on our equal sign. And so it says pick one side of the equation and write it down. Your goal is to transform it so that it looks like the other side. And it's usually easier to start with a more complicated side. And you'll see what we're talking about when we actually do an example. So look at which one of these on each side of the equal sign is more complicated, and usually you want to start by working on that side and leaving the other side alone, not changing it. You're going to use your identities. You're going to use algebra and the identities that we know to change the side that we started with and to bring those expressions to a common denominator, to factor them, to replace them with fundamental identities to simplify our expressions. And then lastly, you want to convert to sines and cosines. If you're stuck, it could be helpful to turn your cotangents into cosine over sine, or your tangents into sine over cosine, or your secants into 1 over cosine. So that is something that we can absolutely do, a technique that we can do as well. So let's see what we're talking about in this three-step process. Let's actually prove an identity. So we're going to consider this equation. Here's an equation that we're going to consider. It is the cosine of theta times the secant of theta minus the cosine of theta, and all of that equals the sine squared of theta. So here is our left-hand side, and here is our right-hand side. Right-hand side. There we go. All right. So I think that the left-hand side looks more complicated. So we're going to start with it and try to transform it to look like the right-hand side. So all we're doing is working on this side. We are not changing anything over here. Every step of the way, our right-hand side looks the same. We're just going to copy it down every step of the way. So we're working on the left-hand side. I'm going to change secant to 1 over cosine. And then I'm going to multiply this term through those parentheses. I'm going to multiply it by that term and then multiply it by that term. Cosine times 1 over cosine gives me 1. Copy down my minus sign. And cosine times cosine gives me cosine squared. And I know from the Pythagorean identity that can be rewritten as sine squared. So see what we did? We totally just worked on the left-hand side of what was going on up here until we used good algebra and good trigonometry, substituting our identities, until we proved that this does indeed equal the sine squared of theta. It equals that right-hand side. All right. So we're going to introduce something extra in this next example that we may need to multiply by or divide by or do something extra besides just change things into sine and cosine so that we can try to manipulate or work mathematically on one side of that equal sign until it looks like the other side. So here they want us to verify this identity. We have the cosine of u over 1 minus the sine of u, and that has to equal the secant of u plus the tangent of u. So we're going to start on the more complicated side. This has a fraction in it, so I'm going to call that more complicated because of that fraction. So I'm going to start turning things into sine and cosine, and you can see already on that left-hand side everything is already in terms of sine and cosine. So that's not going to help me. So I'm going to try to multiply by something so that maybe I can get an identity to show up for me. I'm out of time on this video. The next one will be fairly short, but look for the next video and we'll finish this process.